Hello everyone, welcome to tutorial number 12 in database CSEN 501, which is our last tutorial in this course. In this tutorial, we are going to discuss some topics related to the normalization. We are going to see what is the closure of an attribute, what is the minimal cover, and the algorithm introduced in the lecture to normalize to the third normal form. Okay, what is a closure? A closure is a set of all attributes A such that X implies A in F. In other words, when we, for example, say that we have a relation called T with A, B, C, D, and A, the closure of A, is the set of all attributes such that A implied these attributes. For example, if we say that A implies C and A implies D, so the closure of A will be A, C, D, the attributes where A implies these attributes. This is the closure. How can we get a closure of an attribute? There is an algorithm which is introduced in the lecture to calculate the closure of any attribute. Result equal A, while result changes do for each functional dependency B implies C in F. If B is contained in result, then result union C, and A plus 1 equal the result. Let's take an example to understand this algorithm. Now we have a relation with attributes W, X, Y, Z with these functional dependency, and we want to get the closure of WZ. When we say closure of an attribute, we write it as follow with the plus. So we want to get the closure of WZ. Okay, so the result will be first starting with this attribute, which is WZ. Okay, for each functional dependency B implies C in F, we are going to check each one. W implies Z. Okay, B implies C. If B is contained, then we are going to add the C to the result. So in this case, B and C are W implies Z. Is B contained in the result, which in this case is W included in the result? Actually, yes. So we are going to add the Z. Actually, the Z is already there, so nothing will happen here. Okay, now we will move forward. Check the next one. We are going to check each functional dependency. Y, Z together are found in the result? Actually, no. The Z is found, but the Y is not found. So we cannot add anything to the result. W, Z together are found? Actually, yes. W, Z are found. So we are going to make the result, which is W, Z, union the C in this case, which is Y. So the new result will be W, Z, Y. As long as there is changes, we are going to repeat. Since a Y is added to the set, so the set is changed, so we are going to repeat the whole step. W is contained, Z is contained, so nothing changed. Is Y, Z contained here? Actually now, yes, the Y and Z are there. So we are going to add the X. Now the set will be W, Z, Y, X. WZ contained, add Y, it's already there. There is something happened in the set, so we are going to repeat. The last time we repeat, nothing will happen, so we are going to stop. So the closure now of WZ will be WZ, Y, X, which means that WZ implies W, WZ implies Z, WZ implies Y, WZ implies X. Okay? What is a minimal cover and what is a cover? F is a cover for G, if every functional dependency in G is also in F. Okay? For example, if we have G and F, with functional dependency implies B, C implies D. And in G we have A implies B, C implies D. If the functional dependency here are found there, then F is a cover for G. Okay? In order to check whether F is a cover for G or not, we need to make something. Okay? We should examine each dependency in G and calculate its closure from F. Okay? If the dependency is then found, then they are covered to each other. Let's take an example. Assume that F is made of A implies B, B implies C, AC implies D, and G is made of A implies B, B implies C, A implies D. And we want to check whether F is a cover for G or not. Okay? How to do so? In order to check whether they are equivalent or cover for each other or not, we are going to take the attributes of the left-hand side in F, which are in this case AB and AC. Okay? And get their closures using C. So we are going to get the closure of A using C, the closure of B using C, the closure of AC using G. So we take the left-hand side from here and get their closure from the other set. So A will be there. A implies B, so B will be added. Now, B implies C. Is B found here? Actually, yes. So, C will be added. A implies D. A is found here, so D will be added. So, the closure of A using G will have A, B, C, D. Okay? The closure of B using G. B implies C. Okay? AC, we will have A, C. A implies B, so B will be added. B is there, implies C, C already added. E implies D, so D will be added. Okay? From the closure, we can deduce that A implies B, A implies C, A implies D, and B implies C, and AC implies B, and AC implies D. Okay? Note that all the functional dependencies in F can be deduced from G. Okay, because using G, we obtained this one, which is found here, we obtained this one, which is found here, and we obtained this one. Okay? Now, we want to check the other side. We want to get the left-hand sides of G and get their closure from F to make sure that these dependencies holds here. Okay, now we are going to make the same using F. So we are going to make the left-hand side, which is A, B, A. So we are going to get the closure of A of B using F. Okay? So now we are going to get the closure of A and B using F. Closure of A holds A. Now A implies B, so B will be added. B implies C, so C will be added. AC implies D. We have A and C, so D will be added. Okay? B. B is there. B implies C, so C will be added. A is not there. B is there, and we already added C. A is not there, so we cannot add D. So, from here we can deduce that A implies B, C, D. B implies C. Now we want to check that these dependencies in G are found there. Actually, A implies B is found. A implies B. A implies D is found. And B implies C is found. So F is a cover for G. Okay? It's just a cover. Now, sometimes we want to get the minimal cover. How to get the minimal cover? And when we can say that there is a something in minimal cover for another one. Minimal cover F for a set of functional dependency if F is a cover for G, but no proper subset of F is a cover for G. Okay? So, if they are covered to each other and no proper subset of of F is a cover for G, which means that if we remove dependency there, the relation cannot still hold. How to get the minimal cover? Okay, the first thing is to make all the left hand side single. For example, if we have here A implies BC, we should make it single. Decompose it into A implies B, A implies C. Find H by removing any redundant functional dependency. Make another set and try to remove any redundant functional dependencies. And afterwards, try to minimize the left-hand side if possible. For example, if we have AC, try to minimize it if possible. And repeat again. Let's take an example to understand more. But before taking an example, let's know when it is very important to use a minimal cover. Actually, in the last lecture, you will find an algorithm to decompose into a third normal form. Okay? How does this algorithm work? First, we get the minimal cover for F. And afterwards, for each left-hand sided functional dependency that appears, okay, we make a relation where if X implies A, X will be the key. Okay? After making these relations, if none of the relation contains a key of R, then create one more to contain the attributes of the key. Okay? Let's assume that we are done with the first step of the minimal cover. Now, we have some dependencies. Okay, now the primary key is X, Y together, and after making the minimal cover, we will get these sets of functional dependency. Now, what shall we do? We should make a relation, okay, getting all the right-hand side that belongs to the same X in relation. So we are going to make R1 with X, A, B, where X will be a super key. Relation 2 with Y, C, D. Okay, now after decomposing, we don't have a relation that has the primary key of the original one. So in this case, we are going to make another relation, putting the primary key together with any remaining attributes, which is in this case the A. Okay? Let's take an example of that minimal cover and how to decompose in the third normal form using this algorithm after getting the minimal cover. First, in exercise 2, we want to decide whether the AB is a candidate key or not using the closure. If I get the closure of AB and I found that all attributes are there, then this one is a candidate key, because using these attributes, I can deduce all the other. So the best way to check whether it is a candidate key or not, we can get the closure. Okay, let's do the closure. Now the result have AB. Is AB is found there? Actually, yes. So we are going to add the right hand side C. CD together found there? No. So we are not going to add E. DE is found there? No. So we are not going to add B. Repeat. AB will add C, nothing change. This will not be added, this will not be added. So from AB, I cannot deduce all the other attributes, so this one is not a candidate key. Let's check ABD. 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 Now, AB is there, so we can add C. CD together are there, so we can add E. DE are there, so we can add B, which is already there. So after the first rotation, we can check that all the attributes are found there. So this one can uniquely identify a relation. However, to check whether it's a candidate key or not, we must make sure that any subset of this key cannot be a candidate key. Okay, so let's check the subsets of this key. We should check the closure of AB, of BD, of AD, of ABD, in order to ensure that this is a candidate key. We checked here that this can uniquely identify the relation, but we should make sure that no subset of this key can can uniquely identify this relation, because in this case this will not be a candidate key. Let's check AB. We already done it there, so this one cannot uniquely identify the relation. If we added BD, we don't have AB, so C will not be added. We don't have CD, we don't have DE, so this one is not a candidate key. AD, nothing can be added. A, B, D. Since no one of the subset can uniquely identify a relation, so this one is a candidate key. Let's take another example. This is the example we already solved. We need to check whether F and G are equivalent or not. When we say equivalent, we mean that we need to check if they are covered or not. So the first thing to do is start with the F. Now we are going to get the left hand side of F. A closure, B closure, AC closure. It will be A, and A implies B, so B is added. Sorry, yes, when we get the right hand side of F and get the closure from the other set. Okay, so A implies B, so B is added. B implies C, so C is added. A implies D, so D is added. So from this one, we can deduce that A implies B, and A implies C, and A implies D. So this relation is found. Let's check the other one. B. B implies C from this one. So B implies C is there. Let's check the third one. AC. A implies B, so B is added. B implies C, C is already added. A implies D, so D will be added. So from this one, we can deduce that AC implies D because it is found there. So this one is correct. Let's repeat it for the G. Get the left-hand side, which is AB, and check that these dependencies are found there. To do so, we get the closure of A from F. So A implies B, B is found, so C is added. AC implies D, so D is added. So A implies B is found, and A implies D is found. Let's check B implies C. B closure from F will be B, C, which means that this one holds, so both are equivalent. Okay? Now, we want to get the minimal cover for F. And afterwards, we need to, using the algorithm introduced in the last lecture, decompose into the third normal form. Okay. What are the steps in order to get the minimal cover of a set? Okay. First, make all right-hand side single. 2, find H by removing any redundant FD, functional dependency. Minimize left-hand side as possible. And repeat again. Go back to 2 if needed. Okay? Let's start the this exercise by solving number A, which is the minimal cover. So, first, moving step by step. Make all the right-hand side single. The right-hand side here is single, 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 single. So, this one is already there. Now, we want to check the redundant dependency. How can we do so? Okay? We can do so by checking the closure of each one of them. In other words, okay, how to check the redundancy? Now, we want to check the first one. We need to know whether this is redundant or not. So what we are going to do is to get the closure of BCD, but with removing this one. If the closure will get us A, then this one is redundant, which means that we can deduce the A from BCD without this functional dependency. Okay? So let's do so. We will have B, C, D. BC implies E, BC are found, so E will be added. A is not there, so F is not added. F is not there, so it's not added. C implies D, they are already there. A is not there, so it's not added. So in BCD, we will not find A, which means that this relation is needed and it's not a redundant one. Okay? So now, after checking the closure, we will not find that we will have A if we removed this one. So this one is not a redundant one. Let's move forward. It's not a redundant. BC implies E. Let's get the closure of BC. BC. First, BCD implies A. We cannot add the A because we don't have D. Remove this one till we check. A is not there, so we cannot add F. F is not there, we cannot add G. C is there, so we can add D. A is not there, so we cannot add G. since a change happened, so we should repeat. BCD implies A. BCD implies A, so we can add A. A implies F. A is there, so we can add F. F implies G. F is there, so we can add G. C implies D, they are already there. A implies J, so they are already there. Now, do we have here E? Actually, no. So, we cannot deduce this dependency without having this functional dependency, so this one is not a redundant one. Let's move forward. A, closure. While removing this one. A, nothing can be added here, nothing here. Here, we can here add G. Now repeat again. If there's something we can add, actually no. So, F cannot be deduced from here, so this one is not a redundant and we need it. F implies G. Let's get the closure of F. F is not there. It's not. BCD is not there. BC is not there. A is not there. We remove this. C is not there. A is not there. So it's actually F. So nothing can add the G except this one. So it's not redundant. Okay. C. C closure. B, D are not there. So we cannot add the A. B is not there. So we cannot add the E. A is not there. F is not there. This one is removed. A is not there. So this one is not redundant. Let's check this one. A closure. A. BCD is not there. BC is not there. A is there, so we can add the F. F is there, so we can add the G. C is not there, so we cannot add something. This one is removed in order to check whether it's redundant or not. Now, we can get that A implies G without having this functional dependency, so this one is the redundant one. So, after doing this step, the new relation will be the same, but we are going to remove A implies G. So, the new set in this case will be so the new set in this case will be F equals to BCD implies A, BC implies E, A implies F, F implies G, C implies D, and we are going to remove A implies G. Now we are done with the second step to get the minimal cover. Let's move to the third step, which is simplifying the left-hand side. Okay, in order to minimize the left-hand side, what the steps should be done? We should get each left-hand side, that is a composite key, and try to minimize it as much as possible. Okay, how this step can be done? Let's check together. Okay, as we mentioned, the new F is the same except by removing the last dependency. So the F will be BCD implies A, BC implies E, A implies F, F implies G, C implies D. Okay? Now, let's check the left-hand side that can be reduced. We have BCD together and BC. The other are single attributes, so nothing can be changed here. Okay, we want to check what if we minimize this. Are we going to get the same dependency or not? In order to do so, let's check what are the cases that can in which this one can be minimized. BCD can be minimized to BD, to BC, to CD, to BCD. In order to know whether simplifying this could lead to the same dependency or not, we should try each and every one. Let's start with BC. So we are going to make a new relation called X, and instead of putting BCD implies A, we are going to put BC implies A. BC implies E, A implies F, F implies G, C implies D. Now, we are going to get the closure of BC from F. So, let's get the closure of BC from F. Okay, now D is not there, so we cannot add the A. BC are there, so we are going to add E. A is not there, we are not going to add the F. F is not there. C is there, so we are going to add the D. Now, B, C, D are there, so we are going to add A. So actually, from this, we can deduce that B, C can implies A. So we can replace this with BC. So this replacement can be done. Let's check if the other replacements, okay, can be done. Now, simply, we can check B closure and C closure. B alone. Now, B closure cannot, there is no TD, so we cannot add this. There is no C, so nothing will be added there. So from B, we cannot deduce that it implies A, so this one is not applicable. C closure, C implies D, and nothing else can be added, so this one is not applicable. So the only one from B3 can be added is BC. We should repeat the same steps for BD and CD. Let's check for BD. Now, BD. We cannot add the A because we don't have the C. We cannot add the E because we don't have the C. A cannot be added, F cannot be added, so this replacement cannot be done. Since this one cannot be done, so no need to check the D closure alone. Now, let's check the last one, which is CD. Okay, this can be not done, can not be added, and this one. So this one will end with CD as well, so this replacement cannot be done. So the only thing that can be done is BC. So in this case, we can remove this one and simplify it to BC implies A. Let's repeat again for this one. BC, we can try B alone and C alone. So, B alone. From B alone, can we get the E? Actually, no. So, this one can be not done. From C alone, can we get E? Actually, no. So, this one cannot be minimized. So, the final F set will be as follows. F B C implies A instead of B C D. B C implies E. A implies F. F implies G. C implies D. So this is the minimal cover for F. Now we want to get, using the algorithm, decompose in the third normal form. The steps of algorithm was first to get the minimal cover and then to turn each dependency into relation, okay, by getting the common attribute and putting with them their the attribute that is dependent on them. So the first one will be B, C are 1, which have A and E. Both are primary key. The next one, A, F, where A is a primary key. The next one will be F and G. F is a primary key. And the last one are 4, C and D, where C is a primary key. Do we have a case where there are missing attributes? Actually, no. And we have a relation that is consists of the primary key, which is in this case the BC, because from BC we can get all other attributes. From BC we can get A, from A we can get F, from F we can get G, and from C we can get D. So actually we have a relation which contain the primary key. So in this case, no need to make other relation, and the normalization will lead to these 4 relations. That was it for today, and this was our last tutorial in this course. If you have any question, don't hesitate to contact me. Thank you very much, and good luck in your final exam. Thank you so much.